Welcome to www.admark.com training video number 2 for a program titled Engineering Software. This program has extensive number of algorithms interfacing various sheets. The program was created before 1995 and uploaded online in the beginning for utilization of the internet. The program allows users to input their present processes relative to grinding and hard turning and have a software program configure the process for the application input. It is both a mirror of your present process as well as a product that will give you the data for input for how the software has calculated what is computed to maximize your process. Some people refer to this program as the predictor. It was written in an old product son Microsoft Java. I chose Java in the early 90s because it was safe from hacking. The product is on my server and Java applets are downloaded onto your computer to allow you to interface with the program. When you close the program, you must start over with the next download. It has also allowed me the option of making changes without sending out disks, but uploading to my website long before it was the norm. This product can be purchased for non-recurring subscription of weekly or monthly and an annual recurring subscription on a yearly basis. You are given an ID and a password, and you can download anytime 24/7. First-time users must download the applets, and then your computer is off and running. Any new computer will need this first-time setup. My recommendation is to print as a PDF file and save relative to applications. This way, you can not only use it for other close applications with just minor changes, but keep a running history of the progress you have made on each application over time. Because of the size of this program and a number of different sheets, I'm breaking this presentation up into 3 sheets. This is engineering software number 2. And we're going to do in this program the cylindrical inch, which we're on at the moment, cylindrical metric, and centerless. We'll have a quick overview of that. Now we'll start off with the cylindrical inch program. This is the actual first program that was ever written for this process. Every input that is next to a maroon font, for example, like grinding type. In these cases, you notice there are also white input cells and a bluish type light gray that's a drop-down box. For this, we're going to choose of OD or ID. We've chosen OD. The horsepower we input was 10, and the wheel diameter is 20. I want to bring that up because had we chosen, for example, ID, you'll see that there's a message that comes out that says the wheel is too large for ID, and that's because the wheel diameter here is 20 inch, and the grind diameter is 2.375 inch. So we'll go back to OD, which eliminates that problem. And we have a choice of low concentration or high concentration vitrified CBN or none. And then we can go to the grinding diameter. Our input for that grind diameter, meaning the finished diameter, is 2.375. The grind length is 10 inches. Stock removal per side is 15 thousandths. I purposely set up this grind length at 10 inches, and I'm going to have just a 1 inch thick and 1 inch contact area with the wheel so that you can see with the P line here, which means the actual contact between the wheel and the work is the same as the wheel thickness of 1, that we will need to have a minimum of 10 plunges. But the program can calculate this, and you'll see this as we go along. Material, we have quite a choice, from alloy steels all the way through, including PCB and PCD. And in this case, we're choosing carbon steel. Hardness, we also have a range. In this case, we've picked 55 to 62 Rockwell C. The surface finish is greater than 22. We had a choice of less than 3, 3 to 7. And as I picked 22, you're going to see that the grit size has been anything in this greenish blue area to the right are calculated recommendations. They will not be used And in all the calculations, which we'll go down here quickly, at the bottom of this page, which are all are blue, but rather the input that you enter into all of these sheets were in the white section, not what you have in the suggested area is what we will make the calculations on. So for example, had we gone and said, okay, let's do 8 to 10. Now watch what happens to the suggested grit size when we hit 8 to 10. It suggests a grit size of 270. And as you can see, it tells us that 270 is 5 thousandths, 5 tenths. If we go back to greater than 22, it's at 80. And if we were to change this grit size, say to 270, you see we're only 2 thousandths, 2 tenths. But we're going to keep it at 100. And now you can see what the actual grit size is. This will be used as a calculation based on the choice that you made over here. The abrasive type, it's saying it would be either CBN or aluminum oxide. The bond type is vitrified. Now that's a choice we have. We have metal, plated, resin, or vitrified. And we chose vitrified. The wheel cost in this case is $5,000. Again, I explained the P line. Now the stock removal rate is going to be based on your input on Q prime. The suggested Q prime is 0.5, and we have put that in as the suggested Q prime. If you look down to the plunge rates here, the suggested plunge rates, if we were to change this to say 0.3, you would see a change in these numbers. We're going to go back to 0.5. And the number of like diameters in this case is 1, which allows us to know that we have one diameter that's 10 inches wide, so we need to have 10 plunges. Our option for materials are conventional wheels, which would be aluminum oxide, silicon carbide, CBN, diamond, or a low cont CBN. We're choosing CBN. The balance head required gram centimeters has been determined based on the width of the wheel and the speed. So therefore we know we need only a single plane, and they're recommending 1040 grams centimeter. Again, information that is calculated for you based on your input. The wheel input RPM that I input in this case is 1623. That is calculated out to 894.94. So if we change this, for example, to 2000, you would see it would be up to 10,000 surface foot. We'll go back to the 8600. We've input 135 on the rough for the RPM and finish 270 for the RPM. Again, we can put in whatever we want. I'm just putting in data based on what we say we want versus what the calculated numbers are. The suggested feed rates is 67. I put it in at inches per minute at 79 thousandths. I'm doing an in feed per side for the finish. I'm skipping the spark out, going to the finish feed. We're feeding in at 40 thousandths, in feed per side at 1,000. So we've got a total that will compute out to, if we were to put too much in here, let's say I change this to 2 thousandths from the 1, then you'll see warning, check in feed total. Over here, total in feed exceeds input feed. So it knows what the total amount is relative to the in feed that you introduced, and as that compares to what you say we want to take off in stock removal. In the traverse grinding, because it's always recommended that you do multiple plunges and only traverse to eliminate the traverse lines. Now we could have taken all of these out and put nothing in here and just gone strictly to a rough traverse and a finished traverse, and then the plunge grinding would not have entered. Now you would still have the recommended feed rates, but these would have been 0, and then the calculations at the bottom would have been off of your traverse grinding input data. Had we chosen, I want to show you one other thing. Had we chosen, for example, conventional, we would have then gone away from the norm where it says 125, 250, 375, and zero point 0.5, which are normal depths of CBN and diamond, we would have gone to conventional selected, and now we can put in the usable depth. Because typically with a conventional wheel, depending on the side, you can have up to 2-inch of usable depth per side or 4-inch overall. We'll go back to the CBN. That goes away. We are going to use a rotary diamond in this case. We have a choice of abrasive wheel, which would be typical if we were doing a diamond and a resin bond. Single point for conventional wheels. Diamond nib, used a lot with the resin bond, diamond and CBN. Rotary diamond, which we've chosen, or a roller dresser where we would have a form to plunge in. We've chosen the rotary diamond. We have a 4-inch diameter roll at 6,500 RPM. The suggestion was 6772. And we can go counter-directional or unidirectional. Unidirectional is always the optimal. Had we done counter-directional, it would have said closes face, finer RA. So it tells you based on what you've chosen. That gives us 2/10 per in feet is what we're choosing. It says less than 4/10. The dresser contact width is at 20 thousandths of an inch, wants to be less than 50. The traverse inches per minute, 6.8. We pick 6.5. We have 5 overlaps with a traverse per rotational wheel at 4 thousandths per rev. The data that we've collected based on the information that is in this software computes that we should be able to get with this product and with the amount of material and the size of the part 26 pieces per dress. So therefore, if we don't change that, all the calculations here relative to wheel life, number of pieces have been set up based on the estimated dresses. If we were to change this to say 100, then all the figures would change based on what we put in for that 100, not the 26. We'll go back to the 26, and you can see now we're at 65,000 pieces versus 100, 250,000. Everything changed, but we're going to go back and take that out, and it'll just automatically revert back to the 26. So we are showing that we're running about 0.59 instead of the 0.5 Q prime that was suggested, but that's based on our input of 79 thousandths as opposed to the calculated rate of 0.067 for the suggested 0.5 Q prime. The metal removal for the finish is 0.3, and we have our total plunge time, total traverse time, and even the percentage of abrasive grain per rotation of the work. This is important so that people that can understand if you go over 15%, there's a good chance you'll get what we call pullouts. So it lets you see that, and is really meant for grinding wheel experts that or manufacturers of the wheel to see if there's too much pressure, regardless of it based on the grit size. We could go up and do a little check. Let's say if we change this to 230. Now we're at 23% because the grit size is so much smaller. And that means there's a red light that comes on. It says we have potential problem here. We're back to 11. And the traverse rate, meaning based on the depth of cut relative to the traverse, is at 12%. We're looking at 186.28 seconds to grind, or 3.105 minutes, and it gives us a wheel cost per part of 0.076 cents. Now, we've also set up a page strictly for metric, and everything is the same here. I just wanted to let you see that in this case we have entered everything exactly the same, but in the metric conversion. And when we get to the bottom, it's going to correlate with the 11, the 3.1, the time, the actual cost per part are almost the same. There is a slight difference, and the main difference is because we weren't using conventional, and we had a choice of 3 millimeters, 6 millimeters, 10 millimeters, or 12 millimeters. And the actual comparison between the 12 millimeters, which we chose, versus a cylindrical inch of a half inch would have meant that we would have needed 12.7. So that'll skew this data just a very little bit. The next sheet is centerless. The centerless grinding has a choice of end feed, which would be in feed, or through feed. Same type of setup, various materials. We pick carbon steel. We have all of the same inputs that you've seen before. In this case, we're actually trying to duplicate, so we're at 5Q prime versus the 3. This is the cylindrical metric. When we go to metric versus at 5 versus inch, we're looking at a difference of 10.7 to 1. The centerless is set up in inch. So we go on down, and you'll see the major difference here is we're going to show a blade material. We can choose cast iron, ceramic, hard bronze, PCD, steel. We've chosen carbide. And we get blade angles. We put in 30. We also put in the reg RPM, and that's what creates the number or the traverse, the rotational speed of the part. Unlike cylindrical grinding wheel where the part is turning, the reg wheel is what's creating that. I think I've done a few things here a little different. No, I'm okay. The rough in feed, we're going exactly with the calculated numbers. I guess we aren't. What's happened here is, I think, let's go up. I think my problem is that this should have been 0.5. Now look at the difference between that, because this is an inch and I put it in metric, so that our grit size, our feed rates now do correspond. 5 was the number I had in before, and that was a typo error. And that's where you saw these incredibly inflated numbers, which I just realized why. So you have to be careful with what your inputs are. We move on down, and you'll see, which I did not go with on the other, I should have taken the time, but we have a section that's also under the inch and under the metric. I'll just go down and show you quickly, which is called coolant. So we review this here. Your choices on all three would be water, oil, water soluble, and synthetic. We've chosen water soluble. It calculates out what you need in flow rate and what you need in concentration, and the nozzle relative to the nozzle width, the nozzle opening, and the velocity. So because we're running so slow in GPM relative to what they're recommending, we're only running 87%. And it says scraper fluid recommended, yes. We go over to cylindrical inch, we'll see much difference because we don't have as wide of a wheel. Here we only need to have 23.16 gallons per minute, which we've input. Now we're running over 101%. Big difference between the 6-inch wide wheel and the 1-inch cylindrical wheel. We have a couple of differences at the bottom, where the truing angle setting, and the diamond holder setting, and the reg wheel setting are inputs that are already calculated into the software. And instead of having a book to go check those out, these are settings that's calculated so that your setup people can actually set it up correctly relative to the diamond holder setting, true angle setting, and again, whatever the RPM is needed on the reg wheel to create the part rotational speed. Again, we have the calculations based on this number. We could change this, but we left it at the calculated number of 49 pieces per dress, because this is not a through feed. We do have an option of through feed, but I set this up strictly as an end feed. Had we put it to through feed, you would have seen data coming in under the through feed grinding. Some of it slightly skewed because we have data that's contradictory based on our input in the early portions of this. That concludes this phase of our software, and I would like to have you visit the website at abmark.com. That's www.abmark.com, and take the time to listen to our audio descriptions of what our site has to offer and review each page. Our Pay Products page has a number of products for purchase, and each is in a zip file. And when purchased and opened, always remember to extract all after downloading a zip file. It has an audio for training. Also, each product has a link to a video like this one on YouTube as an additional training tool. If you have any questions or suggestions, please contact me, Dale Savington, at the website www.admart.com from the Contact Us portion of each page.